and there's a little red dot in the bottom there, and now we're recording. So if you watch this first one, we just start talking. Now, when I first started making these videos, I was like, ooh, I'm putting videos up on YouTube, and I should be really, super serious. And it was so boring. I'm sorry. I like to have fun while I teach. So just because we're recording doesn't mean we're not going to have fun. It's going to, you know, sometimes I might put it on mute. And then I'll take it off so that we're, you know, but sometimes I make fun of somebody and I leave it on there because it's fun. Anyways. Yeah. Okay. So, here are the lists that we put our numbers into, right? We had this list of numbers yesterday, frozen, there we go. We had this list of numbers yesterday, and we wanted to put them into groups. What's going to happen today is we're going to see how mathematicians have decided to organize these numbers. And it's a little bit different than we might have thought when you guys were trying to put them into piles, but then you had problems because you felt like some numbers could be in either pile, right? You felt like, you know, what I said yesterday, there's 3, there's 6 divided by 2, or 6 over 2 as a fraction, and there's a square root of 9. And there's like, where should these ones go? Because that's a fraction, but it's equal to 3. That's a square root, but it's equal to 3. I could also write a decimal, 3.0. That's also equal to 3. Ooh, I could make the 0 repeating. Zeros forever. That would still be 3. So now we've got problems with where do we put certain numbers. And we're going to find out from the page that you have there and our notes for today, what are the different families. So you'll notice on your page, I left some things blank for you to fill in. So there's little squares there. So for example, you have the number families, but you don't have these names, so you can start writing in naturals, wholes, and integers. And mathematicians get really fancy with the symbols. So the computer can't do the symbol nice enough. I'm going to get you to write the symbol properly beside it. For natural numbers, they write an N with 2 lines to begin with. Super cool. So when you write an N that way, in mathematics, that means all natural numbers. So what you want to do is you'll want to take in your notes. Does anybody not have a pen or pencil? And in this box, you're going to want to write naturals. And instead of writing the N, we'll write the symbol that way. Okay? Yeah, it's kind of an N with an extra line. It's pretty cool. Now, the natural numbers, the reason they started with those is because historically, or even when you grow up, those are the first numbers you learn. They're your counting numbers. The first things people ever did with numbers was count things, right? And some people say we use a base 10 system because we have 10 fingers, right? If we were born with only 6 fingers, our math might be totally different than what we know right now. So those are our natural numbers. And then there are our whole numbers. Sort of see a theme going on here with the symbols. With the whole numbers, they just added 0. So when we're talking about the number 2, we would say the number 2 is in the category of natural numbers, but it's also in the category of whole numbers. 2 is a natural number, and 2 is a whole number. But in whole numbers, we add zeros. Next, when did you start doing negative numbers? Already in grade 6 or grade 7? Grade 5, maybe? Integers. Now, especially in Winnipeg, we need integers because all winter What are the temperatures? Negatives, right? Boo, winter. That's why the power went out yesterday, right? Because it hit positive temperatures, the power went out, it all went crazy. Now, sometimes, I think this comes from the United States, sometimes in the United States, they use the symbol I for integers, because integers start with I, seems to make sense, right? The international symbol is a Z. It comes from the German word Zahlen, which starts with Z. And it is the international symbol for integers. So integers include all of the natural numbers. They include 0, so they include all of the whole numbers. But now you have your negative whole numbers, which we'll just say those are called integers. And we need them for temperatures, right? Because if it was minus 5 degrees out and the temperature went down 3 degrees, how cold is it now? Minus 8. So you already have an advantage over people that live in warm areas because you know how to work with adding and subtracting negative numbers with temperatures already, right? Let's say you wake up tomorrow morning and it's minus 4 and it goes up 7 degrees during the day. What's the highest? 3. So what you're doing there is you're basically doing minus 4 plus 7 and saying it's equal to 3. But sometimes when we write it like that, it gets confusing for us. But when we put it into the context of, hey, we're thinking about temperatures, then it's easier for us. So that's one of the things I'm going to try to do for you guys during the year. I'll teach you something, the mathematics, but I'll also try to put it into context so you're like, oh, that makes sense, okay? Because sometimes when we do some mathematics, it gets pretty abstract. Okay, next family. The rational numbers. So cool. I like these symbols. Now, the rational numbers are every number that can be expressed as a fraction of integers. And it includes every decimal that stops and every decimal that repeats, which is super cool. Like I said, I like math. I'm already getting excited about repeating decimals. I'll show you in a second, okay? So if you have any fraction, right, 2 divided by 3, that's a rational number. 3 divided by 1 is a fraction. It's a rational number. But can you see that that's also an integer? Yeah. And also a whole number? And also a natural number? Yeah, the story would be like, the store would sort of be set up as a circle. Well, I've got a diagram for the grocery store of buying numbers afterwards. So we'll be able to see what it looks like. Okay? Now, if you have a decimal, 0.3. In middle school, in elementary school, you learned about decimals. Do you know what this place is called? Because like there's ones and tens and hundreds. This is, oh yes, tenths. The wonderful English language who decided to put th at the end of a word. Tenths. So if that's tenths, and we want to write it as a fraction, we have 3 tenths. And it's easy to write any decimal as a fraction if the decimal terminates. So if I would go 0.213, this is tenths, this is hundredths. I'm going to have like spit on the inside of my mask. And this is, wonderful, starts with a th, ends with a th, thousandths. Okay? So since it ends in the thousandths, we can write this as 213 thousandths. And so it's really easy to write any decimal that ends as a fraction. Now, something very cool about repeating decimals. 0.1 repeating. I'll see if you can figure out the pattern. It's 1 over 9. Okay? 0.23 repeated is 23 over 99. 0.1571 repeated, 571 over 999. That's so cool. That is very cool. Oh. Okay, do you want to have your head blown a little bit? Are you ready for mathematics to blow your mind a little bit? Okay. All right. Sorry, you'll find that sometimes I get excited about something, then I get off topic a little. Well, it's sort of on topic, but off topic. And sometimes I might tell stories and what. Are you okay with that? Yeah? Okay. No stories. Keep it just. You love stories? Okay, but which is bigger? 0.9 repeated or 1? 1? 0.9. Oh. She's saying they're the same because if you write this as a fraction, it's 9 over 9. Which I'm not telling you to do this in your science class. That's a little crazy, right? But now, technically, if you were doing a question in science where the answer is a number, like 5, you could technically write, don't do this, then I'll get in trouble if I tell you. You could technically write 4.9 repeated because that's the same as 5.
Yeah, but we're not.
But do you think your science teacher is going to mark you right? No, they're going to be like, wrong. So maybe not a good idea. But the interesting thing is you're initially, when you think about the two, your gut says that 1 is bigger than 0.9 repeated. That's how you feel it should be. It feels like they shouldn't be the same number, even though they are, because 0.9 repeated is 9 over 9, which is the same as 1, last time I checked. But for numbers to be different, anytime you have two different numbers, it's always possible to put a number in between them. And between 0.9 repeating and 1, there's no number that you can put in between them. And so if there's no number that you can put in between them, they're the same number. Okay, that's weird mathematics starting off. Like, mathematics can get weird. That's your weird mathematics to start off. Okay, next family is the irrational numbers, which is usually shown with the same symbol as rational numbers, a Q, with either a bar in front of it or, but this one I tend to see more often. That's probably the one I'm going to use. And when we put a bar over something, sometimes in mathematics that means not. So anything that's not a fraction is an irrational number. Well, if it's not a fraction, that means it has to be a decimal that goes on forever, but it also can't repeat. So it has to go on forever without a pattern. Pi would be an example. Square roots. Square root of 2. You know, it starts off at 1.41 dot, 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 dot. And if we look at our calculator when we type it in, you'll look and say, I don't see any pattern. Then you would say, I think this is an irrational number. The hard part is there might be a pattern of, oh, it repeats itself every 100. Your calculator doesn't show you 100 decimal places. But we'll say that any square root, and it's not all square roots, because why doesn't 9 get included? Because that's equal to 3. So That's a natural number, a whole number, an integer, and a rational number. 3 belongs into 4 families, whereas the square root of 2 belongs into irrational numbers. Okay. And then we don't want the irrational numbers to feel too left out. So we put everything together as the real numbers and say, these are all the numbers that we have. Rational numbers and irrational numbers are sort of the 2 main groups. But then in the rational numbers, we have special subgroups. And then if you go to university, someday down the line, you might learn about another family of numbers. Yep, those are the complex numbers. They include, wait for it, a special kind of number. Okay? It's going to be a little bit of a game. I'm going to start telling you that you have to figure out what this word is. It starts with an I. Yeah, you have to figure, I'm slowly going to give you, so it's not the, yeah, wow, 1 letter. The imaginary numbers. That's amazing. You should play the Wordle of the day today. I think you're ready. The complex numbers include imaginary numbers. Well, they do exist, but they don't exist. Wow. Okay, so I'm blowing your mind now. 2 things in one day. It's like, whoo. Okay. Imaginary numbers let you do things that aren't allowed in real numbers. Like you're not allowed to square root negative numbers. In imaginary numbers, you can. So, well, it's fascinating. What's the purpose of having them? Is there's some things in real life that can't be solved with real numbers. But if we include imaginary numbers and work with them, we can solve problems, and then the numbers come out real again in the end, which is kind of weird. Okay? But that's going higher and higher levels of mathematics. We're going to stick to grade 9, though, this year. We're just, first of all, finding all of these. So if you went to the number superstore for grocery shopping, this is what the superstore would look like. And I'd like you to put a big box around this whole thing. So the whole superstore says, instead of grocery store, it says real number store. You can go in there and buy any number you want. When you get in there, there's 2 main sections. There's the section with the rational numbers and the section with the irrational numbers. So if you know that you need to buy some irrational numbers, you go to that section. If you're like, ooh, I need to get some rational numbers, you go to the rational numbers section. And then the rational numbers section is organized into smaller and smaller rings. So if you're like, I need to buy a 2/3, that would be in the outer ring, which would be available anywhere. But if you needed to buy a -5, the -5 would be in the whole rational number section, but it would be located in the integer section. And picking up the number 5 and putting it in your cart and walking her. Isn't there a gum that has like a 5 on it? 5 gum? Is that what it's called?
It's called 5 gum.
I think 5 Alive is something you drink.
5 gum is called 5 gum.
It's just 5. It's 5 gum, right? It has like big 5 on it. I don't know why. Is it? Yeah. So there's all sorts of groceries you can buy with the number 5. Yes. Yeah. Then there's a whole number section, and then right in the middle would be the counting numbers, your natural numbers, right at the beginning. So what we're going to do as some examples here. First one. Is this?
This is not.
Yeah, you flip your page over. And
Oh
then
wait, I was on the wrong page.
you were on the wrong page. You're good to go. So first of all, we're going to decide if they are rational, and I'm going to put the symbol for rational there, Q, or irrational with the bar over top. So if you went to the number superstore to buy your number groceries, and you were looking for a 3/4, would you go to the rational section or would you go to the irrational section? Rational. What about the square root of 2? Hey, irrational. Bar over top. What about 5.456? Pi. That'd probably be the number one thing you'd go to buy at a grocery store if it was numbers. I think so. 4/9? Rational, because it's a fraction. What about square root of 4? Ooh, it's a sneaky one, right? Because it's equal to 2. Maybe you want to put that beside there. It would just be rational. Nice. All right. He drew a picture of a person shopping for the numbers. I love it. Okay. What about this one? Irrational. So we look, this ... means it keeps going. Do you see it repeating anywhere? No. It's not repeating though. The dots just mean that it keeps going. It never ends. There are numbers that keep going that never end. You know what? I could take my ruler and draw a number that never ends. No. This is, oh. Okay, I'll show you that afterwards. Well, so much good math that we're doing already. So this one would be irrational because it doesn't repeat. Do you see that this one is equal to this? So that one, oh, geez, I never did that. You didn't see that? That one's rational. Okay. Okay, I got off topic again. I'm going to draw, we're going to imagine I zoomed in to some graph paper here, and the graph paper was perfectly 1 centimeter each section. Okay? Would you agree that you could take your ruler out and start from this corner, take your ruler, mine has to be a little bit longer, but I zoomed in, and draw it to this corner? That's possible to do, right? Okay. I just drew a number that's a decimal that never, ever ends. Okay. How long is this? Longer than 2 centimeters. Do you remember doing this in grade 8? How long is this side?
2 centimeters, 1 centimeter. So it would just tiny square. Equals C squared. Yeah, squared and then it choose 4 and then yeah.
So what's C equal to? No, what do you have to do? What's the opposite of squaring?
Which is
Irrational number that goes on forever. But we just drew it.
that's the 3rd time today.
That I've blown my head? Okay. It's all right? All right. It's a good thing. All right. Sounds good. So we just drew a line. We just drew a number that goes on forever, but it actually is an actual length that exists. That's a little bit sometimes confusing and hard to imagine too. All right, sorry. We're going to do lots of a squared plus b squared equals c squared from now until you graduate in grade 12. All right, now let's make a list of our families. Maybe you want to, do you want to draw the circles? I think that's helpful. We got our circle that are our rational numbers, and this circle is our irrational numbers. Then inside, we have our integers, then our whole numbers, and finally, wow, that's not, I got too small too quick. Can you imagine that there's an n in the red one? Here, we'll zoom into that so you can see it. There we go. There's the zoom in of what's in there so we can see what it is. So now we look at 44. Where would 44 be in this whole thing? In the red circle, right? So because it's in the red circle, it's also in the black circle. It's also in the green circle. Oh, sorry, I have to change my green circle. I went all American there. I like the international symbol. And it's also in the rational numbers. And it's also in the whole store. So it's in the reals. So for 44, you'd have to put down all 5 of those. But I think it's easiest to find which specific section it is first and then work your way out rather than starting with reals on, I mean, we could write real, 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 real all the way through. We do, because it says list all the families. So -3, which circle is it in? It's integers, so that's the first one. And then that would also mean, if it's in this circle, it's also in this circle. And that means it's also in the reals. And by the time you graduate in grade 12, you will have written this R more than any of the other letters. Okay, next one. 0. It's in the whole numbers, so we start with that one. And that means it's also in the integer circle, which means it's also in the rational numbers, and it's also a real number. They don't all have to be reals. You figured out an imaginary number. There was an imaginary number. I put one on your sheet at the beginning. We'll go back and look at it. The ones you cut out? There was an imaginary number on there. I'll show you where it is. We'll go back and look at it. 5/9. What's the smallest one it belongs to? Rationals, because it's not an integer. And then that would also mean it's a real. 1.352631354 ... Irrational, no repeating that we can see. Also a real number. Yeah, I like changing colors. You thought it was blue and then your head was going crazy? Yeah, well, it might be. If everybody else could think that this is blue and say it's blue all day, it'll be really good. We'll make Nevaeh think she's going crazy. Yeah, it's blue. Right? Blue, green, black, blue, blue. There we go. You know what? I sometimes, and I shouldn't have or whatever, but I made a joke once about colorblind, and I found out later I had a student in my class who was colorblind, and I felt terrible. But they're colorblind because sometimes I like to highlight stuff for their, oh, that's not working today. They're colorblind, they could not see yellow. So when I would take out my yellow highlighter and highlight stuff, it would just be like I was highlighting in clear paint. They couldn't see it, so I had to change my highlighter color to green. They told me. Yeah, they told me. They're like, I can't see that at all. I'm like, really? Yeah, now my whole, great. See, this is what happens. I did colorblind thing again, and my computer gets mad at me. Maybe it is not responding. So the last one we can do in our heads. Yeah, it's gonna be recording now, probably going like that, and glitching while we're doing it. But if we look at the last one, negative 2.3, that is going to be a rational number and a real number. Okay, well, usually it starts to respond after anywhere between 1 and 25 minutes. So I will give you your homework worksheet to start on so we're not wasting time. And no, and the non-real number that was on your paper, there was the square root of 9, negative 9. That one was not allowed. This is okay, because negative square root of 9 is negative 3. The square root of negative 9 is 3i, where I is an imaginary number of something. Just pretend. Okay, so this is straightforward, just the same thing we just did. You put it into the list. Oh, and it's responded now. But I'll let you try a few, not all of it, and then we'll keep going. I'll just pause the video temporarily. I'm going to get you to turn back to your notes. And in your notes, we're going to look at other families. So the first thing, well, I should maybe hide this, but it's already showing. Looking at the numbers, could you tell that those are called prime numbers?
Yes.
So, yes. So in mathematics, we have our number families for organizing them, but then there's also special families that come up as well that they name things. Prime numbers is an example. Okay? And there's lots of different numbers that have got grouped together, special patterns that happen. So we're only going to look at a couple of them. Prime numbers come up quite a bit. So what makes something a prime number? You can only multiply it by itself and 1. Now, that's an important little tiny definition, because notice that the number 1 is not included. Lots of people think that the number 1 is a prime number, but it isn't multiplied by 1 and something else. So 1 is its own special thing. The first prime number is 2. So that's your first weird thing, because many people would say 1 is a prime number, but it's not. Sometimes called its own special thing, unity, whatever. Next one's perfect numbers. And this is just for fun. You'll never probably have any question ever in a math class that says, use a perfect number to do so and so. But a perfect number is a number where you figure out everything that can divide by it except for itself and add it up. Would you agree that you can divide 6 by 1? You can divide 6 by 2, and you can divide 6 by 3. And since you add up 1 plus 2 plus 3 and it equals 6, they call it a perfect number. And it's interesting that the perfect numbers, there's not very many of them. 6 is the first one. 28 is the second, but there are only 4 less than 10,000. And if you Google it, you could find higher ones. So there are some people, there are some competitions out there amongst mathematicians is who can find the highest prime number. And if you find the highest prime number, then everybody's like, ooh, crazy mathematics that this person figured out. Who can find the highest perfect number? Well, there's probably keeps getting higher and higher. But there's only been 4 found less than 10,000. So it's kind of interesting. Yeah, you can Google it, find out more. Next ones, palindrome numbers. Now, they're not that exciting, but I find them more exciting in English. A palindrome number is a number that you write it forward or backwards is exactly the same. They are way more fun in English. Can you think of any sentences that you could write that when you say it forward and backwards, it's the same? Oh, never mind. Level is that's a good word. Anna is a palindrome name. Or Hannah. Hmm? Race car. Okay. Here's the only sentence that I know. Well, it's not a sentence, it's more of a statement. A plan. Panama. Panama is a country. They have a very famous canal through Panama, which connects the Atlantic and the Pacific Ocean. Oh. Oh, shoot, I thought it worked. Oh. A pan? Okay, I'll have to look at. Anyways, you can also look up famous palindromes. That one was close, but I forgot exactly how it worked. Shoot. Okay, that is where we are going to stop for our lesson today, except I have an interesting, well, I think it's interesting, booklet for you to work on if you. What was the word? A man? A canal. That makes it even better. A man, a plan, a canal, because that's the famous thing, Panama. The sea. This right. Canal. Panama. A canal.
No, it can't be an O. There has to be an A.
That is an A. You're just making fun of my writing. That is an A. Robber. Yeah, I know. Say it again. I'm a lasagna hog. Okay, well, that's. It's technically a sentence. Okay. Next thing I was handing out, and I had it in my hand. Here it is. Oh. First, okay, before I hand it out, I have a puzzle for you. Here's your puzzle. Yep. You have the numbers. You were allowed the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 to 9. You've done one of these? It's a magic square. You have to put the numbers in the square, magically, so that every row adds up to the same thing, every column adds up to the same thing, and every diagonal adds up to the same thing. And then I'll tell you a story.
But you can only have one of each number, right?
You can only have one of each number.
I'll do it later.
No, you have to do it now because then I give you a handout, and if I give you the handout, then the answer's on there, and then it's like, oh.
Okay. Yeah, that's where the internet comes in handy.
Hey, don't internet it.